Okay, moving on to question 3 of common test 1. Okay, so question 3 basically is again a periodic table question, but the focus is now on the halogens, alright, group 17 halogens. So in this case, we're looking at group 17 hydrides, where you have your HF, HCl, HBr, and HI. You're given the boiling points, as well as the observation when heated. Now, so the first question is explain why the boiling points of HCl, HBr, and HI increases down the group. Now, there's a very big misconception here that surfaced from this test. Now, when we look at boiling and melting, so I use HX in general. When we look at boiling and melting point, we are not breaking the HX bond. Alright, we are breaking the IMF between the HX bonds. So boiling, melting, these are physical process. We are only targeting the IMF. But when we try to do heating to reduce it to brown and violet vapor, this, of course, all of us know it's a bromine gas and your iodine gas. Alright, in this case, when we're doing heating, we are looking at thermal decomposition. In this case, what are we breaking? We are breaking the HX bond. So in this case, thermal decomposition, we are breaking the covalent bond. Okay. So when you look at boiling point, down the group, there's an increase in boiling point. So down the group, what changes? The size of the electron cloud. So if the size of the electron cloud gets bigger and bigger down the group, naturally, your extent of IDID will increase down the group, and therefore, you require more energy to overcome the intermolecular IDID. So that's why HI, being the largest electron cloud, the electron cloud is the most polarizable, most distorted, and therefore you have the most extensive IDID. Okay, so for 1 mark, these are the 2 marking points: size of the electron cloud, weak intermolecular IDID. Alright, for 2 marks, then of course these 4 points. Okay. Now, the boiling point of HF is significantly higher than those of the others. Most of you could correctly identify the hydrogen bond as the main reason, but the way you guys draw the hydrogen bond is atrocious. It's as though you guys never learned anything from J1. So recall, in hydrogen bond, you need a delta plus H and F, O, and N. Alright, so the delta plus H attached to F, O, and N. So in the hydrogen bond, I need to see a pair of dipole. I need to see the delta plus H, the delta plus on the H forming the hydrogen bond. And because it exists a pair, I must put as a delta plus and a delta minus. Indicate the lone pairs and label the hydrogen bond. So the 3 things to take note of in drawing hydrogen bond. This is something that you're supposed to have been well drilled by in JC1. Alright, and this bond between H and F in the molecule, these are covalent bonds. I shouldn't be seeing dotted lines in between H and F atoms in the molecule. Okay, moving on. In part 3, we look at when it's heated. So in this case, we are looking at thermal decomposition. Now, this thermal decomposition question was very poorly attempted. Many of you talk about polarization, charge density, extent of polarization. Charge density and extent of anion cloud polarization is in your group 2. It has nothing to do with group 17. So you need to know what are the different trends, different explanation for a different group. Group 17, the concept of charge density and distortion of anion electron cloud is not applicable here because we are not looking at an ionic compound. In group 17 hydrides, all these compounds are covalent, they are simple molecular. So as I mentioned, we are breaking the covalent bonds. So as the HX bond strength decreases due to poorer extent of orbital overlap, so we require less energy, and as a result, the thermal stability of a group 17 hydride decreases from HCl to HI. And this is the trend that you observe in the observation, because for HF and HCl, on even strong heating, F2 and Cl2 is not formed. But strong heating will produce Br2, and moderate heating will already produce your iodine gas, which means the HX bond in HI is a lot weaker than HBr, which is in turn a lot weaker than HCl and HF. Okay? Okay, this done. Let's move on to part B then. Now in part B, we have sodium thiosulfate. Now, if you know thiosulfate is S2O32 minus. Okay, and then reacting with bromine and iodine. So what's the role of bromine and iodine? If you look at this reaction, bromine is in the oxidation state 0, bromide is -1. So same thing, iodine 0, -1. If you look at the oxidation state of sulfur in S2O32 minus, it should be in the +2 oxidation state, +2 oxidation state. In the case of this sulfur over here is +6, and in the case of S4062 minus, the peroxide disulfate, it's +2.5. So you can see that basically this essentially is a redox reaction. Your halogens, bromine and iodine are functioning as your oxidizing agent because it oxidizes your sulfur from thiosulfate to something else. Alright, increases the oxidation state of sulfur. So in this case, because the extent of change in oxidation number for the case of iodine is only from +2 to +2.5, the change is smaller, and therefore you can conclude iodine is a weaker oxidizing agent as the oxidation number only increases from +2 to +2.5. Okay, so you need to indicate what's the change in the oxidation number, and you need to tell me in what species. This is a standard template that we have taught you guys in redox. Okay, so to compare reducing strength or oxidizing strength, you always need to compare the change in the oxidation number. Okay, now in part 2, let's take a look at what's happened in part 2. Part 2, again, many of you, either due to lack of time or have very poor reading skill. So we have excess aqueous barium nitrate added to the resulting solution from reaction 1. So let's take a look at reaction 1. What's the resulting reaction? Okay, so reaction 1, we have bromide, sulfate, and H+. When we add barium nitrate, what will react? Alright, you have your barium sulfate, which is the white PPT. Okay, so barium sulfate is in the white PPT. What else passes through the filtrate? The filtrate will therefore contain NO3 minus, Br minus, and H+. Okay, nitrate from the barium nitrate, Br minus from the earlier part of reaction 1, and H+ from reaction 1. The question says that when aqueous silver nitrate is added, a cream precipitate is formed. So what is this cream precipitate? It must be your silver bromide, AgBr. And this is further confirmed that it's soluble in excess corn ammonia to give a color solution. Now then we go in the context of the question. The question asks you to explain for the formation and the solubility of the cream PPT. Did the question ask for the white PPT? No, so there's no point in you explaining the entire process from the first paragraph because the question did not require you to do so, and therefore you lose precious time and you do not get any credit for it. So the equation to write will therefore be the solubility of AgBr. AgBr, as we all know, it's a sparingly soluble salt. It will dissociate to form Ag plus and Br minus partially, alright, because it's sparingly soluble salt. Okay. What happens when corn ammonia is added? Now, when corn ammonia is added, we know that it forms a soluble complex, and this is the silver diamine complex that we have been talking about during the tutorial and in lecture. Alright, so your halide test, you get in practical 2 when you saw your silver chloride dissolving because you form your silver diamine complex. Now, when this done, this is form, what happens is that you use up Ag plus, and therefore your Ag plus in equilibrium 1 will therefore decrease. Okay, your concentration of Ag plus will therefore decrease. So if Ag plus concentration decreases, the question now is how will the system then react? The system will therefore respond by shifting equilibrium position in 1 to the left. To do what? To try to increase Ag plus. However, Ag plus will still be used up to form your complex, and therefore overall Ag plus still decrease. Okay, so what happens when Ag plus decrease? We'll explain why the PPT dissolve, right? Why the solubility of PPT, right? Why does it dissolve? So to talk about why PPT dissolve, we always have to compare between ionic product and KSP. So, because silver plus decrease, as a result, mathematically, ionic product will decrease to a smaller value. When this value falls to a value below the KSP value, the cream PBT will therefore dissolve or be soluble. Okay, so this entire phrasing is not invented for this question. This entire phrasing is straight from your solubility equilibrium lecture notes. Direct copy and paste. Okay, so if you can't do this question, it just shows how well your bookwork is. Right? You need to spend time to understand the concept and try to internalize and get used to the technical terms. Okay, that's question 3. I will discuss MCQ in the last video.